So let's recall what we did so far. So we talk about 4 different models in the previous discussion. So what are the 4 models? So the first one was dy over dt equal ky. So this works for the exponential decay and exponential growth depending on whether k is positive or negative. So the solution was y equal a naught e to the kt. T is the independent variable, so I use kt. If the independent variable is x, it is kx. So this is actually 2 situations. If k is positive, so this is the exponential growth situation, so like that. And if k is negative, this is the exponential decay, so it's going to go like that. Okay, the same solution depending on k positive or negative. And then we talk about the simple harmonic motion situation. It's a second order differential equation. So it's d squared y over dt squared, let's use time as the independent variable, so negative k squared y. So if this is the case, then what we do is we're gonna get y equal a constant cosine kt plus another constant sine kt. And then the third one, d squared y over dt squared equal positive, so it's a k squared y but positive. So in this case there are 2 type of solutions. So one is a e kt plus and then b e negative kt. So this is the kind of the hybrid of exponential growth and decay. There's another solution. You can write the same one in this form, a constant. So this a has nothing to do with the previous a. Okay, a constant cos kt plus another constant sin kt. So that's the it's the same the solution you can write in 2 different forms. You can show that they are equivalent. You can start with one and you can get the other one, but you will not get the same a. I just use a as a constant. Okay, so this is what we did so far. So these are what we call the 4 fundamental models. So there are 2 for one for exponential growth, another for exponential decay, and then simple harmonic motion, and then the what we call the hybrid model. Good. So now what we're gonna do, we're gonna go to we can study especially the first type. So what we call the first order differential equation. So let's talk about that. So so we're gonna spend time for that now. So we're gonna discuss this in kind of detail. First order equations. So so if you look at a first order equation, so it looks like that. So a first order equation, first order, that means the degree, the derivative is the first derivative. A first order equation, first order ordinary differential equation, you can say is an equation of the form dy over dx equal a function of x and y. So it can be function of both the independent and the dependent variable. Or in simply we can write this one as y prime equal fxy. Okay, So this is a this is how a first order differential equation looks like. So so the goal is to how to handle this kind of differential equation. So let's just have a kind of look at a simple situation. So how about this problem? So let's say consider yx equal x cube plus sin x minus 1. By differentiating if you take the derivative with respect to x, what are you going to get? Y prime equal, you're going to get 3x squared plus cosine x plus 0. Okay, so and you can see that, so I'm going to call this is a star. You can see that this is a differential equation. Okay, so this is a differential equation. This is a differential equation, and you can see that it is very easy to solve this equation. So you have a differential equation now, but it is very easy to solve. What do you do? Because you take the derivative to get the equation star. So that if you want to go back, what do you do? Just integrate, is that right? Because you do the opposite process. So you can see that a solution of this equation, of this differential equation, is what? Because you know that once you take, because you take the derivative and you get this one, so that if you integrate, you're going to go back. So, okay, a solution, like one solution. Okay, a solution of this differential equation is, you can say that is yx equal x3 plus sin x minus 1, because that's what you get if you go back. Okay, because that's how you start with. But you can see that you really don't need to say you're going to get -1 as the constant, because we don't know, because when you take the integral, it can be anything. So in general, we can say, any solution, in general, any solution of the form, so in general, any solution of the form yx equal x3 plus sin x plus c, where c is a constant, okay, where c is a constant, is a solution, to the star equation. So this is something we need to understand. So you can see that, so if you start with a different like a function, you can take the derivative and you get a differential equation. But when you have the differential, if you want to solve it, that means you want to find a function that satisfies the differential equation. How to do that? Normally you just take the integral. Once you integrate, you're going to get the original function. But the thing is that you really don't get the original function, because you get the general situation here. You don't get -1 when you go back. So what's going to happen? Instead, you get a function with the constant in there, and then to find that constant, you might need to use some initial conditions. Okay, so we can say all right, to find c, we use some conditions. It's depending on how many constants we have, so conditions. Okay, So but you normally get this as the solution. So let's have a look at it, this situation, you know, how we can do it and when you can just integrate and get the solution. So let's look at this in two different ways. So what we're gonna do, we can do the type 1. Okay, I'm gonna break this into two types. So we're gonna say type 1. Type 1. So what is type 1? So let's say, so what we have is we had y prime equal fxy. So type 1 means because you know there's this function fxy is a function of two variables, but the first type is it is just a function of the x variable only. Okay, so that's a type 1. So we can say so assume, just assumption, assume fxy equal yx is fx. Okay, that means only depend on only depends on the x variable or the independent variable. Okay, x, that means the independent variable. Okay, so that's the first situation. So we assume that your fxy function is only depend on the independent variable. So that means your differential equation now becomes y prime equal fx. So that's the situation we try to handle first. It's a function of only the independent variable. So what we can do in this case, we can just integrate. Okay, so because so we have so then we can say by integrating with respect to x. Okay, x, that's the independent variable. By integrating with respect to x, what we have is so you can integrate both sides. So it's a y prime, you can get dx, and the integral of fx dx. But we know that when you integrate the derivative, you get the function back. So you're going to get yx on this side, the other side you're going to get fx dx. Okay, so you don't want to add plus c here because plus c is already included in the integral. So that's the solution in this case. Okay, so we end up getting this as the solution. Good. Now so we can say so this is the general solution. This is the general solution. Which contains an unknown c. Okay, so this there is a c, but we normally don't write it because the definite integral contains a unknown. Okay, so I'm going to write a small note here. The definite integral contains an unknown c. Okay, so it will be clear once we do some problems. So and also let's write a small note again. The most general general antiderivative. So this is the actual antiderivative. Most general antiderivative is known as the definite integral. Indefinite integral, not the definite integral, is known as the indefinite integral. Indefinite integral. Is known as the indefinite indefinite integral. It's called indefinite integral, and use the notation fx dx. Very good. Okay, so so this is the first situation. So what's the first situation? You can see that the fxy function is a function of the independent variable only. Okay, it's a function of the independent variable only, and then what you can do is you can simply integrate both sides. You simply integrate both sides with respect to the variable x, and you get the solution. So that's the easy way to do it. So let's look at few examples just to see how things gonna work. So we're gonna do this example. So let's say example 1. So find the general solution of y prime equal 3x squared. Okay, y prime equal 3x squared. So so this is an easy problem. So we have y prime equal 3x squared. So integrating both sides, integrating both sides, we have y with derivative. So if you integrate, you get y equal the integral of 3x squared dx. So this is an easy integral. So we have 3 times x3 over 3 plus c, which is equals to x3 plus c. Okay, good. So where c is a constant, and this is the general solution. As you can see, it's like very simple, just integrate. So let's look at another example. Example number 2. Find the solution of y prime equal 3x squared plus sin x minus ex such that y0 equal to. So these kind of problems, what are the problem? It has a differential equation and a condition, but you can see the condition start at 0. So these kind of problems are what we normally call initial value problems. Okay, these problems are called initial value, because this is initial, it's at 0. These problems are called initial value problems. Initial value problems. Okay, initial value problems. So the answer to this is y prime equal 3x squared plus sin x minus So what we have, yeah, I'm gonna like a slight modification. Let's put a yeah, so yeah, let's make a slight modification to the problem. So what I'm going to do, I'm going to put a 4 here and a 2 there, just to get do a little bit more. So I slightly change the problem. Okay, so change, it is 4e 2x. Okay, now what we can do, and we can see that this is also the same situation. You can see that the function is a, you can see this side, this is just a function of x only. X means the independent variable only. If it's independent variable only, you simply integrate to the two sides. So let's do that. Okay, so if you integrate two sides, so so by integrating, we're going to get y on this side. The other side, it simply becomes 3 x3 over 3 plus integral of sine is negative cosine. Okay, integral of sine is negative cosine, and then minus 4 e to the 2x divided by 2 plus c, a constant. So if you simplify this a little bit, you're going to get x3 minus cosine x minus 2e2x plus c. Okay, good. So this is the general solution. You can see there's a constant there. So this is the general solution. So this is the general solution. This is the general solution. Now what we can do, we can use the initial condition to find c. Okay, so let's do that. Since y0 equal to, we get 2 equal 0 cube minus cosine 0 minus 2e0 plus c. We know that the cosine 0 is 1, e to the 0 is also 1, so you're going to get negative 1, negative 2 plus c, and you can solve this, and once you solve this, you're going to get c equal 5. C equal 5. So therefore, you can get y, which is a function of x, equal x3 minus cosine x minus 2e2x plus 5. Okay, so that's the solution to the initial value problem. That's the solution to the initial value problem. And then let's look at like another form of the solution, because sometimes this form is also useful when you try to solve certain problems. So another form of the solution. Another form of the solution. Another form of the solution. Suppose y prime x equal fx. Suppose y prime x equal fx with y x naught equal y naught. X naught may or may not be 0. That's not really necessary sometimes. So let's say you start with this general problem. Okay, so we have a differential equation, first order differential equation, along with a initial condition. Now what we can do, as before, we can integrate. Okay, so integrating from, now what we can do, we can integrate from x0 to x, because those are the limits of integration, because we know that when you integrate, you can have a general x, or you can integrate only in a specific domain. So that's exactly what we can do. We can integrate in this one. That means we just try to find the area between these two lines. Okay, so there's a curve somewhere, so we just try to find the area below it. So that's what we're trying to do, just that part. Okay, so let's do that. So if you do that, so we can start with y prime equal fx. That's your problem that you have. So if once you integrate this side, you're going to get yx, because that's the derivative. But now we have limits. So what are the limits? The x has to start with x0 to x. Okay, the same thing, integral fx, so dx, but what's going to happen, it has to go from x0 to x. But you know, for theoretical purposes, just to avoid confusion, we are not going to use x here, because we had to use something else just to avoid the confusion. Okay, so what we normally call the we use a dummy variable. Okay, dummy variable, but something other than x. So what we know, so the best way to write this one is x0 to x, if let's say s or something. Okay, just use something other than x just to avoid confusion. Okay, so that's what you get. And from the other side, you're gonna get, if you plug in this one, it's gonna be yx minus yx0. That's what you get on this side. And then here it's gonna be x0 to x, and then fs ds. Okay, now what we can do is, actually I want to tell you something. So these kind of x's are what we normally call the dummy variable. Okay, dummy variable. So we call this is a dummy variable. Dummy variable. So so what happened? So we have this one. Now let's move the yx0 term to the other side. So if you move yx0 to the other side, you're gonna get y equal yx0, but yx0 is y0. Okay, plus the x0 to x fs ds. So you can use this as a formula. So this is a formula for the general first order differential equation. Okay, so that's the solution. And you can see where the x0 goes and where the y0 goes. Okay, so that's the solution. So you can use this as a formula if you want. Yeah, so I'm going to call this equation number 2. Okay, equation number 2. Good. So we had a previous one. Let's go back, and I'm going to call that equation number 1. Yeah, so this is equation number 1. So this, let's call this equation number 1 for our future purposes. And but here c is in there. Okay, but once you integrate, you get the c, otherwise you don't see it. And the next one is so we're going to solve this equation, and you end up getting this one as the solution. Okay, so let's verify that whether that's actually the case, because you don't make sure that when you plug in x0, you're gonna get y0. Let's see. So it can be seen that when x equal x0, y x0 equal y0 plus x0 to x0 fs ds. And you can see that what is x0 to x0 means. So if you look at this as a situation, so that's x0. So that means the integral doesn't go anywhere. It's can stuck at x0. That means the value of this integral is simply 0. Okay, so this is simply 0, that means you simply end up getting y naught. So that means you can satisfy the condition. So you can see you end up getting y naught. When you say y, if you evaluate y x naught, you get y naught. So that satisfies the condition. Okay. So so this is like, what you can do, like in general, so if you have an integral, you have a differential equation where y prime is a function of the independent variable only. So what you can do is you can integrate. But there are some situations where you cannot actually find the solution in the closed form. So let's write it. So there are situations. Okay, there are situations. Okay, there are situations in which we cannot solve. We cannot. Okay, we cannot solve an ODE. We cannot solve an ODE, even PD. Okay, we can solve an ODE in closed form. In closed form. That means expressed as an algebraic expression, as an algebraic expression. Okay, without integrals or derivatives. Okay, without integrals or derivatives or anything else, just the algebraic expression. So let's write without integrals or derivatives in the solution. Okay, So so let's look at a situation. So let's look at this problem. So let's say solve y prime equal e to the minus x squared along with y0 equal 1. Okay, solve y prime equal e to the x squared with y0 equal 1. So this is a situation where you can use the formula if you want directly. So let's use that. Okay, just to see. So according to the formula, so what we have yx equal y naught plus x naught to x fs ds. So if you plug in here, y naught is 1 plus starting with 0 to x. So we have e to the minus s squared ds. Is that right? E to the minus x squared ds. But this is a very interesting integral actually. This is one of the very common problem in mathematics. This is what we call the Gaussian distribution formula. But unfortunately, this is something that you cannot integrate. Okay, so it can be shown that, or we can say it has been shown that, there is no closed form solution. It has been shown that there is no closed form solution to this problem. There's no closed form solution to this problem. So what we can do, we can leave this as the answer. Okay, so we leave I want to say double star. We leave equation double star as the answer. So what you can do is, if you get a problem like that, so you can solve this any further. So what you do, you can do numerical calculations. Okay, so you can use a calculator or a computer or something like that, and you can numerically calculate, and we can discuss some of those techniques in this class as well. So yeah, so there are two methods we can discuss. We can use what we call the Euler method or the Runge-Kutta method. From using those two, we can numerically calculate this one. And also, this integral is very important for statistics. So this integral is very important. Is very important in statistics. This is what we normally call the error function. Have you heard about the error function? Error function. Okay. So this is actually the error function. So what the error function is? So the notation is ERFX. Okay. So the error function is, it is 2 over square root pi. So there's a constant, interesting constant. That's what we call the normalizing factor. It's going to go from 0 to x, and then it is e to the negative x squared ds. Okay. So what is this? So you can see it's the same integral, but go from 0 to x. So what is this? This is an area. It's an area represented by this. So you're gonna graph the normal curve. That's what we call the normal curve, bell curve. And what you're trying to do, you can start with 0 and try to find the area up to x. You try to find the area up to x. So that's what we're trying to do. So this area is the value of the error function. Okay, value of the error function. That means at 0 is 0, and then it's going to increase on that side. So that's the error function, ERFX, and that's x. Good. So this is very useful, and what so you can find these values in tables. Okay. So find the values in tables. Okay, find the values in tables. Good. Okay, so now what we're gonna do, let's talk about the second type. Okay, the second type. So what's the second type? So what's the second type? Okay, so far, so what we have, I'm going to write this one in summary. If the y prime equal fx, the independent variable, you're going to get y equal the integral of fx. Okay, just integrate. Now let's talk about type 2. So what is type 2? Type 2, which is y prime equal fy. Y prime equal fy. Okay. Y prime equal fy. So that means a function of the dependent variable. Okay, is a function of the dependent variable. Okay, function of the dependent variable. So you can see that this time, so let's try this one in Leibniz form. So if you use the Leibniz form, this is dy over dx equal fy. So the problem is we cannot integrate as we did before, because the problem is, you can see on the right side it is a function of y, so you cannot integrate with respect to x. So that's a problem now. Okay, so the difficulty is this. So let's say, so if you just try to integrate this on the two sides with respect to x, so you're going to get fy dx. So that is not possible, because this part you cannot do, because it's a function of y but the variable is x. So you can't do that. It has to be the same variable before you integrate. So that means this is where we get stuck. Okay, so you cannot do the way we did before. So what you gonna, but we have a workaround. What we're gonna do now, we don't write the formula like that, but we're gonna make it upside down. Okay, that's an interesting trick. So so rewriting as, what we can do, we're going to make it upside down. We can write this one as dx over dy equal 1 over fy. Okay, we can do that assuming fy not equal to 0. So if you assume that fy not equal to 0, you can make it upside down. Now you can see that this is exactly the version that we had before. This is a type 1 situation, because you can see now you can just assume that your independent variable is y now. Okay, so this level you can do that, but once you talk about advanced classes, you need to really worry about what's really going on here and when you can do it and when you can't do it. But the problem that we discuss in this class doesn't create much problem here, but we still discuss that a little bit. Okay, so what we did was we make it upside down. Once you make it upside down and change the variables from x to y, just treat y as the independent variable. Okay, so I'm going to write this one, treat y as the independent variable. Okay, so treat y as the independent variable. So in this case, now it's simply become a type 1 problem, because once you make it upside down, now y is the independent variable, so the other side is just a function of the independent variable, so you can integrate. Okay, so now what we can do, we can integrate with respect to y now. So integrating with respect to y, what are you going to get? So this get x, you get x now, because you can integrate with respect to y. Okay, so you can x, but which is a function of y, equal the integral of so you can write dx over dy. Okay, that's exactly the same thing, and this equals the integral of the other side. It is 1 over fy dy. Okay, you can see that that's going to give you a formula. So the formula is xy, we just write y just to exaggerate what's going on here, and this is 1 over fy dy. Okay, 1 over fy dy. So this we're going to consider as the formula now in the type 2 situation. What do? You're going to make it, you're going to flip it, make it upside down, and then integrate with respect to the other variable. Okay, and we don't add the c here, because c already contained inside the integral. Okay, now what we can do, after we integrate, we try to solve for y if we can. Okay, so let's say solve for y if possible. Okay, solve for y if possible. Solve for y if possible. Good. Okay, so let's try to look at some problems to understand the argument. So good. So let's look at the first example of this type. So example, solve. So let's say solve y prime equal ky. Yeah, k is a constant. Yeah, k is a constant. Because we know that y cannot be 0, but because of that we need to check whether y is a solution. If y is a solution, there is a problem. But so let's look at the answer. So first note that y equals 0 is a solution. Why y equals 0 is a solution? Since if you take the derivative, which is 0, so that means the derivative is 0, y equals 0. So if you plug in, it works. Okay, so that's the reason. So y equals 0 is a solution because the derivative is derivative y prime equals 0. So that's a solution. Now assume that it is not equal to 0, just to find other solution. Okay, assume. So we try to find all the non-zero solution now. Assume y not equal to 0. The goal is to find non-zero solution. Okay, so to find, let's say to find non-zero or non-trivial non-zero solutions. Okay, but zero solution is like useless, you know, so you can't do much with that. So we try to find non-zero solution. So we assume y not equal to 0. Okay, assume y not equal to 0. So if y not equal to 0, now what you can do is your differential equation is dy over dx equal ky. What you can do, we can make it upside down. So we can write dx over dy equal 1 over ky. Okay, now what we can do, integrating with respect to y. Okay, integrating with respect to y, we're gonna get xy, which is the integral of 1 over ky dy, and which is 1 over k. If you integrate okay, it's 1 over y dy, so it is 1 over k. Integral of 1 over y means ln y, but don't forget the plus c. Okay, that's the plus c. See, that's where the constant coming. Okay, let's see. Now what we can do, we need to simplify the rest. I mean, if you can, we try to solve for y. You don't have to, but normally like you need to solve for y equal, because that's what someone asking. So how to do that? You're going to multiply both sides by k. So you can write this equation as ln y equal kx minus kc. So this says that y equal e to the kx minus kc. Now what we're going to use in simple algebra, we can write this one as e to the negative kc e to the kx. Now what we can do, we're going to consider this whole thing just simply a. Okay, just a constant. That means this is going to be a. Actually, before we do that, we can remove the absolute sign. We forgot that. So let's remove the absolute sign. What will happen when you remove the absolute sign? When you remove the absolute value sign, what's going to happen? You're going to get plus or minus c. Actually, it would be better we do it in a different step. So I'm going to do that differently. So let's erase this. Okay, erase that. So we have y equal absolute y equal that. So now what we're gonna do, we're gonna remove the absolute sign. So once you remove the absolute sign, you're gonna get y equal plus or minus e to the negative kc e to the kx. And this whole thing is just a constant. We're gonna call it a. Okay, once you call it a, you're gonna get this one as a e to the kx. Okay, where a is a constant, a constant, and you can see that. So that's the general solution. Okay, which contains a, and that's the general solution. Now what we can know, remember we had a solution y equals 0. Let's see whether y equals 0 solution is already contained in there. So let's do that. So so you can see the solution. Okay, the solution y equals 0 corresponds to a equals 0. Okay, so that means it's already there. So therefore the general solution is y equal a e kx. Okay, here a is a constant. Here a is a constant. So you can see that it's not that difficult, but you have to think a little bit. Okay, so let's look at another example. So how about this? Find the general solution of y prime equal y squared. So the answer is again, let's see whether, because you need to make it upside down, so you again always need to check whether that term is not equal to 0. Okay, so as before, so first note that y equals 0 is a solution. Why? If you plug in y equals 0, it works, because y prime equal to 0, so 0 equals 0, it works. So now we assume that y not equal to 0. So then what we can do, we can write the equation upside down. So dx over dy, which is 1 over y squared. Now integrating with respect to y, you're going to get x equal the integral of 1 over y squared dy. So this is very easy to integrate. When you have 1 over y squared, what are you going to do? So I'm going to do the integral here just to show you what's going on here. So it is 1 over y squared dy. You can write this one as y to the negative 2 dy. Now we just use the power rule. When you use the power rule, you're going to get what are you going to get? You're going to get y to the negative 1 divided by negative 1 plus c. Okay, so in other words, negative 1 over y. Okay, negative 1 over y. So it's become negative 1 over y plus c. So now the question is how to solve this. It's very easy to solve. You can bring the c to the other side. So this one you can write as negative 1 over y equal x minus c. So if you solve for y, you're going to get y equal, just flip it and change the sign. So it is get 1 over c minus x. Okay, and c a constant. Okay, so this is what happened actually. So but now this is very interesting, because remember in the last time y equals 0 solution contained in the general solution, but now you can see that for no value you ever get y equals 0. So that means so let's try this. So note that this solution does not contain y equals 0. Hence the general solution is y equal 1 over c minus x or y equals 0. So you have to write it like that, because there are two different solutions, and y equals 0 does not contain in the other solution. So there are two solutions. If you just write one, it's not the complete solution, because there is a solution that you cannot represent using that form. Okay, that's very interesting. And then you can also see that this solution doesn't exist when c equal x. Okay, so let's see what's going to happen if x equals to 1. Okay, so let's just look at it like a special situation. So if x equals to 1, this is how the solution, like if you look at the graph, this is how it looks like. So x equal 1 looks like this. So this is a special situation. So let's say if c equal 1, we get this graph. So this is the c equal 1 situation. So you can see in the c equal 1 situation, so you're gonna get this what they call a vertical asymptote. Okay, vertical asymptote. So that means when the function try to reach the value 1, the graph gonna goes to positive infinity from the left side, negative infinity from the right side. So that means at x equal 1, the solution does not exist. So that's very interesting. At x equal 1, the solution does not exist. So that means there is no continuous solution for this problem. So these are what we call singular solutions. Okay, these kind of solutions are what we normally call singular solutions, because it doesn't exist at all the points. Okay, so let's so I think it's very clear. So so let's write about that. So not. Okay, so the solution does not exist. Okay, does not exist. The solution does not exist when x equals c. Okay, x equals c. In the graph, it is x equal 1. Okay, x equal 1 because c equal 1. So here c is equals to 1. So that's the special case we are trying to do here. Good. So the solution does not exist when x equals c. So we say that there is a singularity. There is a singularity at x equal c. There is a singularity at x equals c. So so if for example, okay, if for example x equal 1 c equal 1, the solution what we normally call blows up. The solution blows up when x reaches 1. So it was very clear in the graph. So you can see that when x try to reach 1 from the two sides, from the left side or the right side, and you can see that the solution goes to infinity. So these are what we call blow up solutions. Okay, so if it is a system, it's gonna kind of break at this point, because if the energy is going to go to infinity at this moment. Okay, so that's what we call blow up, because it's going to go to infinity either direction. Okay, good. Called blow up solutions when x goes to 1. So as a result, the solution exists only in the solution exists only in the domain, okay, in the interval, we can see only in the interval -1 to -infinity to 1 union 1 to infinity. So you can see that 1 is excluded, okay, 1 is excluded. So that's the domain of the function. Okay, so if you look at this one, so the domain is, so we numerate the curly y. So the domain of y is simply -infinity all the way up to 1, the union 1 to infinity. Good. So let's look at a few other examples. Okay, let's look at some other examples. So there's more examples. So let's say find a solution of y prime equal cosine y. How about this? Such that, let's say y0 equals 0. Okay, y0 equals 0. And you can see that this is a type 2 problem because it's not a function of x, it's a function of y. So the answer, rewriting dx over dy, so you're gonna get 1 over cosine y because we write it upside down. So this is secant y. Okay, 1 over cosine y means secant y. Now what we can do, we can integrate. How to integrate? So integrate with respect to y. Okay, so integrate with respect to y. So if you do that, what are you going to get? This side you're going to get x, which is a function of y. This is the integral of secant x, secant y in this case. So what's the integral of secant? It is in the table of integrals. So from the table of integrals, this simply becomes natural log secant y plus tan y plus c. Okay, so that is the integral. Okay, it's coming from the table. So let's say use table of integrals. Okay, use table of integrals. Now what we can do, so that's a c, and then as we discussed earlier, to find the c we can use the initial condition. Okay, so let's use the condition now. So we're gonna see since y0 equals 0, we're gonna get 0 equal x0 equal natural log secant 0 tan 0. So remember these are y values, okay, plus c. So so let's exaggerate a little bit. So that is the y value, right? And then so this is the x value because it's going to go backward. It's x equal function of y. Okay, so y value goes there, and this is again the y value because y equals 0. Since y equals 0, we put the y value there. Okay, good. Now what this says that if you evaluate this, what is secant 0 equal to? Secant 0 equals to 1, tan 0 equals 0. So that means you're going to get ln 1 plus c. How much? Ln 1. Ln also equal to 0. So you're going to get c equal 0. So this says that c equals 0. C equals 0. So therefore your solution is simply ln secant y plus tan y. Okay, and you can see that you have to solve for y, but y is inside this one, so it is you can, but it's not that easy. Okay, so but what we normally call these are implicit solution, not explicit solution, but implicit solution, because the solution is in there but inside the equation. So you can say this gives y as an implicit function. Implicit function of x, as an implicit function of x. Implicit function of x. So I'm going to give you this as a problem. See whether you can do this. Okay, you can solve for him. So try to find. Okay, try to find or try to solve. Okay, try to find. I say try to solve for x. So try to solve for y. Okay, see whether you can do that. It's not. It's not impossible. You can do it, but see whether you can do it. Okay, so this is like interesting example. Interesting example. Okay, so let's do one more example. Okay, yeah. So I'm planning to do like 2 more examples. So let's say find the general solution of y prime equal y squared minus y minus 2. Okay, find the general solution of y prime equal, doesn't look like prime, y prime equal y squared minus y minus 2. So this problem is also very similar, but there's a factoring here. So how to do this? So what we're going to factor that first. Okay, so note that. Okay, note that y squared minus y minus 2 equal y minus 2 y plus 1. Okay, those are 2 factors. Thus y equal 2 minus 1 are solutions. Since y prime equals 0 in both cases. Okay, so you can see if you plug in that, if you take the derivative is a constant, if you take the derivative is 0. So if you plug in that, you're going to see that both sides equal to 0. That means a solution. Now what we can do, we can assume that to find the other solutions, we assume that y not equal to any of those numbers. Okay, so then what we have dy over dx, which is equals to y minus 2 y plus 1. Now what we can do, we can make it upside down. Once you make it upside down, you're going to get dx over dy equal 1 over y minus 2 y plus 1. Now you can see this is just type 2, so we can integrate both sides with respect to y. Okay, so that we can do. So let's do that. Integrate with respect to y. So if you do that, it is x to the x a function of y, the integral of 1 over y minus 2 y plus 1 dy. How to integrate this? You know that to integrate this, you have to use the integration by parts, not integration by parts, partial fraction method. Okay, so we're going to use partial fraction method. Partial fraction method. Okay, so we can use the partial fraction method. To do that, we can write this one as partial fraction, so the y minus 2 y plus 1, which is a over y minus 2 plus b over y plus 1. Now what we can do, we're going to cross multiply by the common denominator, so you can write this one as 1 equal a y plus 1 plus b y minus 2. So the substitution method is the easiest for this kind of problems, so we can use a substitute. Remember we discussed so how to do that. To find a, substitute the other one, that means substitute y equal 2. Okay, if you plug in y equal 2, you're going to get 1, you get a. If you put y equal 2, it is 2 plus 1, and you can see that this is simply 0. Now this is going to give you a equal 1/3. Now do the same trick, so we can substitute the other one. So when is y equal, what's the other one? Negative 1. Okay, negative. Once you plug in negative 1, it is 1 equal 0. That's the whole point, is getting a 0, and b negative 1, so it's a negative 1, negative 2. It's going to give you b equal negative 1/3. Okay, so we find two numbers there. Now what we can do is we can plug in them, so that means your solution becomes x equal the integral of 1/3 y minus 2 minus 1/3 y plus 1 dy. Take the 1/3 out, then you can integrate this one, so you get ln y minus 2 minus 1/3 out ln y plus 1 plus c, and you can combine them into 1. Okay, now so this is a solution. Okay, this gives y as a implicit function of x. Okay, so this gives y as an implicit function, of x. This gives y as an implicit function of x. But let's see, this is an interesting exercise. Let's see whether you can actually solve for y. Okay, so let's see whether we can solve for y. So I'm going to do it. So what we have, so let's try. We can do more. Okay, we can do more. So what we're trying to do, we try to solve for y. So let's start with the problem. So it's x equal 1/3 ln y minus 2 y plus 1 plus c, and then what you can do is you can multiply by 3, so it's a 3x minus c, which is ln y minus 2 y plus 1. Now this is exponential function. We try to write this using this is a log function. We try to write them using exponential function. So we can write this one as y minus 2 y plus 1 equal plus or minus, because we removed absolute sign, e to the 3x minus c, and as we normally do, this is plus or minus e to the negative c e to the 3x. We're going to take this whole thing as a, so this simply becomes a e 3x. Now how to solve for y? Okay, to solve for y, what we can do is we can cross multiply the two, so we can write this one as y minus 2 equal if you multiply both sides of y plus 1 times a e 3x. If you distribute this, you get ay e to the 3x plus a e 3x. Now what we can do, we can take all the y terms to one side, the other terms to the other side. So if you take all the y terms to one side, you're gonna get, what are you gonna get? You're gonna get y minus ay e to the 3x, and if you move the 2 to the other side, you're going to get 2 plus ae 3x. Now if you take y as a factor and divide by that factor, you're going to get y equal 2 plus ae 3x divided by 1 minus ae 3x. Okay, I hope this is clear. Okay, so you can see that's a solution. Okay, that's a y as a function of x. So sometimes you can do that. Okay, so sometimes it's really difficult, sometimes it's impossible. So there are cases like it's doable or difficult or impossible. There are all three cases. Okay, now how to find a? We use some initial conditions to find a. Okay, so so it can be found. Okay, it can be found by, we can say using initial conditions, using initial conditions. We don't do that here. Okay, using initial conditions such as, something like y0 equal, just give a number. Okay, and then just try to find a. Okay, so that you can do. Okay, good. So let's talk about one practical situation and how to use these kind of things in real life situations. So let's just do that one, and then that's the end of this discussion. Okay, so the applications. Okay, applications. So let's say, so let's look at an example. Suppose a car, that's not a car, so let's write car again. Suppose a car drives at a speed e to the t over 2 meters per second, where t is in seconds. Okay, here t is in seconds. So the question is, how far did the car go? Okay, how far did the car go in 2 seconds? In 2 seconds, starting at t equals 0. Starting at t equals 0. So the question is how far it moved from t equals 0 to t equal 2. So t equal 0 to t equal 2. So the question is how far the car go during that time. What is the distance? Okay, so this is like a simple a calculus problem. So you can see, so let's do it in the proper way. So let's say let x denote, okay, let's x denote the distance. Let's x denote the distance the car traveled. Okay, so then the equation we can write as x prime equal e to the t over 2, because they give the speed, so that's the first derivative, which is equal to e to the t over 2. Now what we can do? Simple integration. Okay, integrating, we're going to get xt, which is equal to integral of t over 2 dt. This is very easy to integrate using the table. So what you can do, you divide by the constant. So it's e t over 2 constant is 1/2, so divide by that plus c. Divide means multiply, so e t over 2 plus c. Okay, so that's the general solution, but we need to find the c. Okay, to find the c we can use the condition, because we find how far it go from 0 to t equals 0, so that means we assume that at t equals 0 the distance is 0. Okay, so to find c we're going to use x0 equals 0, because we can find how far it go between the two. So the 0 equal x0 equal 2e 0 plus c. This is 2 plus c. This says that c equal -2. Okay, so c equal -2. Now what we can do is we're going to get xt equal 2e t over 2 minus 2. So that's the distance. It's in meters. Okay, it's in meters, so it's in meters. Okay, now what do you want to do? We need to know how what's the distance at t equal 2, so we can just plug in t equal 2. Okay. So so we can do that. So taking t equal 2, okay, taking t equal 2, we have x2 equal 2e t over 2 minus 2, which is approximately 3.44 meters. Okay, if you use a calculator you can see that it's approximately 3.44. we normally write up to 2 decimal places. That's like common practice. Okay, so in summary, so what we have, so let's write what we have. Okay, so in summary, the first one we have is if y prime equals fx, you're gonna get y equal the integral of fx dx. Number 2, if y prime equal fy, what do you do? It is x, you upside down, you make it upside down and integrate with respect to y. We normally don't write the c because c already contained in there. So those are the two formulas. And also we have y prime equal fx with the condition y x naught equal y naught has the solution y equal y naught plus the integral going from x naught to x f s ds. Okay, so you can use this formula, you can use this as a formula so directly. Okay, so this is a summary of what we did in this discussion.